It is possible to build a container ship by stacking the containers in groups of 10. So there'd be 2 from front to back and 5 from side to side. 2 times 40 is 80 feet long, 5 times 8 is 40 feet wide. So they'd be in a stack that's 80 by 40 feet. The stacks would be 5 high, and then there would be a support beam deck level to separate each group of those 5 stacks, and that is to prevent damage to the containers. The higher the stack of containers is, the more likely the container at the bottom is to be damaged by the loading, particularly with the movement of a ship at sea. Every year, there are containers that are crushed by the load and containers fall off the ship. It doesn't happen that often, but it does happen. The groups of 5 containers in the levels and the beam support levels would then be placed down into a vertical tube from the top of the ship. The ship would look something like an auto carrier. The actual tubes with the containers would extend down to the tank level at the bottom of the ship, the underside of the ship where you have fuel tanks and water tanks. Above the engine room, the stack of containers would have to be lower because you need a space to have the engines. At the top of the tubes could be sliding hatches, and those hatches would prevent the containers from being exposed to rainwater and seawater. For the ship to achieve its designed efficiency, there would need to be specialized cranes and handling equipment at the dockside to lift the containers in groups of 10, and then move them onto perhaps a self-driving platform. The platform could be electrically powered. On the underside of the platform could be wheels in pairs that could turn 360 degrees so that the platform can maneuver in very tight spaces and maneuver very easily. When the containers moved onto the platform would drive off to another area where the individual containers would then be moved onto trucks, trains, or put into stacks of containers for temporary storage. When one platform drives off, another platform would drive in, the process would be repeated. At some point, platforms with 10 containers on them would drive in, and they would then be used to refill the tube stacks, the stacks of containers. The most valuable real estate in a harbor is the space where the ships come in for loading and unloading. The faster you can transfer cargo, the more profitable the harbor can become. The problem with civilian shipping of containers in this design is that the ship is heavier. There is more structure to the ship weighs more per container, which means more fuel burn. The ship is also probably going to carry fewer containers. All that means the cost of shipping per container is higher. You have faster transfer times at the dock, you have less containers being lost from damage. That may never actually offset the increased cost of fuel. The design is only intended to work for full levels of cargo containers. If you don't have a full 10 containers, you have to put empty containers as spacer blocks to make the whole system work. The other problem with this design is it's designed only for 40-foot long containers. There are 45 and 53-foot long containers. If you wanted to carry 45 or 53-foot containers, you'd have to put them essentially at one end of the platform. At the other end of the platform, the only thing you could put are 20-foot long containers. And again, if you can't evenly level them, you'd have to put empty containers in to fill the space. There is a fair amount of dead space with the larger containers. Part of the cranes that pick up the containers could have adjustable or adaptable positions to pick up the containers so they can actually handle the different lengths of containers. There are also containers of different heights. The standard container is 8.5 feet high. There are some containers that are 9.5 feet high. You would have to have an entire level of 9.5-foot containers for the stacking to go smoothly. And again, you'd have to put empty containers in place if you can't get enough containers of that size and description. For the military, the ships could also be used to ship vehicles as well as containers. You could use those same beam support levels for the containers and use them to put layers of vehicles. In that case, you might want to make them half width. So instead of being 80 by 40 feet, they would be 80 by 20 feet. And that entire support beam plus the vehicles would be picked up and put down along the side of the ship, and the vehicles would then be unloaded. It can also, of course, carry logistics containers for the military. And in fact, you could even have a mixed cargo of both vehicles and logistics containers if you so wanted. With a military ship, the cargo cranes would probably have to be mounted on the top of the ship. That way, there's no danger of arriving in a port and not having the handling equipment to remove those racks and levels of equipment and vehicles. But when you put the cranes at the top of the ship, you're adding weight at the highest point of the ship, which is a stability consideration. And the cranes are exposed to seawater and the movement of the ship, and so there may be some questions about the reliability of the cranes. For civilian usage, it could also carry vehicles. The problem is it's not efficient. You have an 80-foot long rigid length. If you had vehicles that were 16 feet long, you couldn't get 5 of them in. You could only get 4 of them. And that means you have a lot of dead and empty space. In a conventional auto carrier, cars are packed essentially bumper to bumper down the whole length of the ship. That makes use of the space in a much more efficient manner. With this design, you can alter the height at which the cars are carried. You could put it a little bit lower for lower cars, but it is doubtful you could ever make up the cargo capacity and the vehicle capacity for having those rigid 80-foot lengths.